In this lecture, we're going to talk about solving systems of equations using the method of substitution. In order to do that, we're going to have to remind ourselves what a system of equations is. A system of equations is a collection of two or more equations considered simultaneously. When we say we're considering the equation simultaneously, we're saying that the solutions must make all of the equations true. A solution to a system of equations is a set of inputs for the variables which makes every equation in the system true. In this video, we're going to be focusing on systems of two equations with two variables. And if a system of two equations with variables x and y has a solution x equals a and y equals b, then we write the solution as the ordered pair a comma b. Before we talk about the method of substitution, let's make sure we understand what we mean by a solution to a system. So here we've got a pretty simple system. It says consider the system of equations x plus y equals 10 and x minus y equals 2. And the notation that you see to the left, this big set brace, is a common way to indicate that this is a system of equations, that we're considering the equations at the same time. There's a question asked here. Is the ordered pair 8, 2 a solution to this system? That is, does the input 8 for x and 2 for y make every equation true? Well, when we check it in the first equation, we get 8 plus 2 is equal to 10, and yeah, that's true. In the second equation, we get 8 minus 2 equals 2. That's a false statement. That's not true. And so while 8, 2 makes the first equation true, it doesn't make every equation true, and therefore 8, 2 is not a solution. 8, 2 is a solution to the first equation, but it's not a solution to the system because in a system we consider the equations simultaneously, and 8, 2 does not solve the second equation. What about 6, 4? Is 6, 4 a solution to this system? Let's test it. So is 6 plus 4 equal to 10? Yes. And is 6 minus 4 equal to 2? Yes. So 6, 4 is a solution to this system. And it turns out it's the only solution. If we interpret this geometrically, what we're looking at is the intersection of two lines. X plus y equals 10 would look something like this. X minus y equals 2 would point in the other direction, and these two lines can only intersect at one point. We're saying that the intersection point is the point 6, 4. So it's pretty straightforward to check to see if an ordered pair is a solution to a system of two equations with two unknowns. But how do you find the solution? Like in this example, we're just told solve the system of equations y equals 2x plus 3 and 5x minus 2y equals 11. Geometrically, we could solve this by graphing these two lines and seeing if they intersect. If they intersect at one point, that one point is the solution. If these two lines are parallel, then there's no solution. And if these two equations happen to be the same line, then there are infinitely many solutions. But drawing this by hand isn't going to be very accurate without graphing paper, so we want to take an algebraic approach. And the basic idea is that we're going to use the method of substitution. We know that in the first line, the y-coordinate is always equal to 2 times the x-coordinate plus 3. Well, at the point of intersection, that would have to be true in the second equation as well. And so what we can do is we can replace the y in the second equation with its equivalent from the first equation, which is 2x plus 3. So instead of 5 times x minus 2 times y equals 11, we'll substitute in its equivalent 2x plus 3, and now we have an equation in one variable. We can solve this for x. 5x minus 4x minus 6 equals 11, x minus 6 equals 11, x equals 17. And now we know that x equals 17. I can let x equal 17 in either equation because it should be the same solution. So for example, I can put it in the first equation, and I get y equals 2 times 17 plus 3, which is 37. So our solution is 17, 37. Now that clearly works in the first equation because that's how we got the 37. We substituted into the first equation. Does 17, 37 really make the second equation true? Well, let's check. 5 times 17 minus 2 times 37 is supposed to be 11. That's 85 minus 74. Yeah, that's 11. It makes both equations true, and therefore it's the solution. It's got to be the only solution because these two lines don't have the same slope. Lines with different slopes intersect at exactly one point. So that is the only solution, 17, 37. Let's solve another system that's a little more complicated. Solve the system of equations x equals 2y squared minus 3 and x plus y equals 0. So here we have a parabola that opens to the side and a line. So if you envision the intersection of a parabola that opens to the right and a line, it's possible that that line could touch twice. It's possible that the line could just touch once if it's tangent to the parabola. And of course the line could just completely miss the parabola altogether. So we might have two solutions, we might have one solution, we might have no solutions. And again, trying to do this by graphing would be complicated without graphing paper. Certainly wouldn't be accurate. And so we're going to do this algebraically. We know that the x value in the first equation is equal to 2 times the y value squared minus 3. And since we're considering these equations simultaneously, that same relationship must hold in the second equation. So I'm going to replace the x in the second equation with its equivalent from the first equation, which is 2y squared minus 3. So instead of x plus y equals 0, we get 2y squared minus 3 plus y equals 0. And now we have a quadratic equation that would probably be more comfortable solving if we put the terms in descending order. See, this should factor 2y times y to get 2y squared, 3 times 1 to get 3, and if it was a plus 3 and a minus 1, then we would get plus y in the middle. And so we get two y values, y equals negative 3 halves, or y equals 1. So it looks like this is that scenario where the line touches the parabola twice. How do we get the corresponding x coordinates? We just substitute twice, and you can plug into either equation, and here it might actually be easier to use the second equation. While it does take a little bit of algebra here, the algebra is pretty simple. So I would actually substitute into the second equation. So I'm going to let y equal negative 3 halves in the second equation, and I get x minus 3 halves equals 0, so that's x equals 3 halves. So one solution is the ordered pair 3 halves comma negative 3 halves. Notice the x coordinate goes first, the y coordinate goes in second. I could also let y equal 1 in the second equation, and I get x plus 1 equals 0, so x equals negative 1. So the solution negative 1 comma 1 also solves the system. If we wanted to check, there'd be no reason to check these in the second equation because that's how we generated these. We would just check these in the first equation since we haven't made sure that it satisfies that one. So in our first two examples, there was a pretty straightforward substitution because one of the equations was explicitly solved for one of the variables. In our first example, the y was already alone in the first equation. In the second example, the x was already alone in the first equation. What do you do if none of the variables are alone in either equation? Well, one option is an alternative method we're going to talk about later. But the other way to think about it is to just create a substitution. We can alter either one of these equations and solve for either variable. My advice would be to find the easiest one to solve for. So in this example, I think it would be easiest to solve for the y in the first equation. Solving for any of the other terms would require a division step that I don't need here. So the first thing I'm going to do is solve for y in the first equation. So if 3x plus y is equal to negative 5, then y equals negative 3x minus 5 when I subtract. Now I have a substitution. So I can replace the y in the second equation with its equivalent from the first equation, which is negative 3x minus 5. So I get 4 times negative 3x minus 5 minus 10x equals 2. And now we'll just solve this for x. We get negative 12x minus 20 minus 10x equals 2. Collecting like terms, we get negative 22x, and adding 20 to both sides, we get 22. So x is equal to negative 1. Now we back substitute to find y. I could let x equal negative 1 in the first equation or the second equation. That wouldn't be too difficult, but it's actually going to be easiest for me to do it in my substitution equation here. So if I let x equal negative 1 in the substitution equation, I get y equals negative 3 times negative 1 minus 5, which is 3 minus 5, which is negative 2. So our solution is negative 1 comma negative 2. If you check that in the first equation, we get 3 times -1 is -3, minus 2 is -5. And we were pretty sure it was going to work there because that's where the substitution equation came from. It's the second equation where maybe we're not sure. 4 times -2, that's -8, minus 10 times -1, that's 10. -8 plus 10 is 2. -1, -2 is the only solution. The geometric interpretation here is the intersection of two lines with different slopes, so it's not surprising that there's only one solution. Here we've got the system x squared plus y squared equals 100 and x minus 2y equals -10. The first equation is a circle. It's a circle of radius 10 centered about the origin. The second equation is a line, and that line might pass through the circle twice, or it might be tangent to the circle and just touch it once like this, or it could be completely outside the circle. So there could be two solutions, there could be one solution, there could be no solutions. We have no immediate substitution, but I hope you can see that it's going to be pretty easy to solve for the x in the second equation. It wouldn't be too hard to solve for the y in the second equation, but that's going to give me a fraction that I can avoid if I solve for x. Solving for x or y in the first equation is going to be much more complicated because we're going to have to consider cases when we take square roots, and we don't want to go through all of that. So I'm going to solve for x in the second equation. Again, you just want to find the one that's going to be the easiest to solve for. So if x minus 2y equals -10, then x equals 2y minus 10 if we add 2y to both sides. Now we're ready to substitute. We're going to replace the x in the first equation with its equivalent, 2y minus 10. So we get 2y minus 10 squared plus y squared equals 100. That's 4y squared minus 40y. Don't forget that you have to get a minus 20y and a minus 20y from the FOIL procedure. Plus 100 plus y squared equals 100. Collecting like terms, we get 5y squared minus 40y plus 100 equals 100. This is quadratic, so we want 0 on one side. And that actually cancels the constant term. So we factor out the 5y and we get y minus 8. And so we get two possible y values, y equals 0 or y equals 8. I'm going to take these and plug them into the substitution equation to get the x value. You could certainly go back to the unaltered version of the second equation to do that. You want to be careful about plugging back into the circle because you're going to get multiple solutions. For each y coordinate, you're going to get two possible x coordinates, but only one of those would work in the line. So it's safer to go to the line than it is to go to the circle. If we let y equals 0 in the substitution equation, we get x equals 2 times 0 minus 10. So that's -10. So the solution is -10 comma 0. X coordinate first, y coordinate second. If we let y equal 8 in the substitution equation, we get x equals 2 times 8 minus 10, which is 6. So that's the solution, 6 comma 8. -10 squared plus 0 squared really is 100. 6 squared is 36, 8 squared is 64, 36 plus 64, also 100. And again, we anticipate that these work in the line because the substitution equation came from the line. So this is that scenario where the line passes through the circle twice. One more example, and this might be beyond something that you've seen before. This says solve the system of equations x cubed plus 4y squared equals 31 and 2x cubed minus 7y squared equals 47. Here, solving for x or y explicitly is going to be a little bit of a pain because you're going to wind up with a radical no matter what. However, there's no rule that says you have to substitute x or y. You can substitute a function of x or a function of y. I notice that it's going to be easy to solve for x cubed in the first equation, and there's an x cubed that I can replace in the second equation. So rather than solving for x, I'm going to solve for x cubed in the first equation. So if x cubed plus 4y squared is equal to 31, then solving for x cubed, I get x cubed equals 31 minus 4y squared. That expression, 31 minus 4y squared, must be equal to x cubed in the second equation as well. So I'm going to replace the x cubed in the second equation with its equivalent from the first equation, which was 31 minus 4y squared. So instead of 2 times x cubed, I get 2 times 31 minus 4y squared minus 7y squared equals 47. Distributing, I get 62 minus 8y squared minus 7y squared equals 47. Collecting like terms, I get negative 15y squared plus 62 equals 47. So negative 15y squared equals negative 15 when I subtract 62 from both sides. Dividing both sides by negative 15, I get y squared equals 1. And so y equals plus or minus 1. Now that we've got a couple of proposed y coordinates, we need to come up with the x coordinates, but we're kind of out of space here, so let me transfer the important information onto another slide. Okay, so we've got our proposed values of y equals plus or minus 1, and our substitution equation was x cubed equals 31 minus 4y squared. I'm going to let y equal negative 1 in the substitution equation first. So I get x cubed equals 31 minus 4 times negative 1 squared. That's x cubed equals 31 minus 4, which is 27. And if x cubed equals 27, the only real solution of that is x equals 3. So we're saying that 3 negative 1 should be a solution. Now we'll let y equal 1 in the substitution equation. And we get x cubed equals 31 minus 4 times 1 squared. Well, that's also 27. And so x equals 3 here as well. So 3 comma 1. Those certainly work in the first equation because that's where our substitution came from. Do these actually work in the second equation? Well, let's see. 2 times 3 cubed minus 7 times negative 1 squared is supposed to be equal to 47. 3 cubed is 27, times 2 is 54. Negative 1 squared is 1, times 7 is 7. And 54 minus 7 is 47. What about 3 comma positive 1? Well, positive 1 squared is also 1, so we're also going to get 47. So these do both happen to work. You might notice that I skipped over the geometrical interpretation of these. These aren't graphs that we would be familiar with. So it's harder to describe the scenario since we don't have the experience with graphs like this. But we did show that these two graphs intersect at 2 points. I want to end with one traditional application problem. Very standard, you've probably done one like this before. It says a rectangle has perimeter 25 meters and an area of 36 square meters. Find the dimensions of the rectangle. With geometric style problems, I like to draw a picture. And I'm going to call the dimensions x and y, but you can give them the more traditional labels of L and W if you want to. If the perimeter is 25, then the sum of all 4 sides is 25. So 2x plus 2y is equal to 25. We also know that the area has to be 36, which means that x times y has to be equal to 36, and there's our system of equations. You'll notice that we don't have a straightforward substitution. We could either solve for x or y in the first equation, that would be pretty straightforward, or we could solve for x or y in the second equation, and I'm going to do that just because it looks a little bit different. We haven't seen anything like this. So just to be a little different, I'm going to solve for y in the second equation. I know that x times y equals 36, so if I solve for y, I would divide by x and get 36 over x. Now I make my substitution. I'm going to replace y with 36 over x in the first equation. And that gives me 2x plus 2 times 36 over x equals 25. So that's 2x plus 72 over x. When you multiply by 2, you only multiply the numerator by 2, equals 25. And let me transfer this to another slide. To solve an equation like this, we'd multiply every term by that denominator to clear out the denominator. That would cancel here. And we get 2x squared plus 72 equals 25x. This is quadratic, so we get 0 on one side. And we get 2x times x to get 2x squared. And when I break up the 72, I need to break it into an even number and an odd number because the middle term is odd. So one obvious choice for that is 8 and 9. And I know I don't want to put the 8 here, because if I put the 8 here, I could factor out a 2, but I can't factor a 2 out of the original. So it would be a mistake to try an even number next to the 2x. I need an even number over here, an odd number here, 8 times 9. And look at that, that gives me 16x on the outside and 9x on the inside. If those were both negative, then I get x equals 9 halves, or x equals 8. So now we need to find the y values, but some of you might have guessed this. The y value that corresponds to each solution is going to be the other solution. It's just a matter of whether x is the short side or the long side. But I'll prove that to you by going back to the substitution equation. Our substitution equation was y equals 36 divided by x. If I let x equal 9 halves in the substitution equation, I get that y equals 36 over 9 halves, which is 36 times 2 ninths. 9 goes into 36 4 times. 4 times 2 is 8. And we get that when x is 9 halves, y is 8. If I let x equal 8 in the substitution equation, then I get y equals 36 over 8. The numerator and denominator are both divisible by 4. 36 divided by 4 is 9. 8 divided by 4 is 2. And I get 9 halves. So when x is 8, y is 9 halves. And as we predicted, these two solutions really go together. It's just a matter of whether x is the short side or if x is the long side. That ends our introduction or refresher to the substitution method. If you have questions about any examples in this video or any examples that you're trying on your own, please reach out to me. You can catch me in an office hour or you can send me some emails.